All right, in this video, I want to talk about how we actually detect planets around other stars. The generic term we use for a planet that's in another planetary system that's not our planetary system is an exoplanet. Exo meaning out of, so planets around other stars, other planetary systems are called exoplanets. And we've only recently, in the past couple of decades, been able to detect more than a handful of planets around other stars. This past 15 years or so has really been a golden age in the discovery of exoplanets. We know much more about what is possible in terms of the structure of other planetary systems than we did when I was a college student in, say, the early 1990s. You might think that the easiest thing to do would just be to build a really powerful telescope that's powerful enough to see little planets around other stars. And that's possible, but it is difficult because even if you had a star that had a planet, stars are really bright. And seeing a tiny, tiny planet next to a very bright star is very, very difficult. It's like trying to see what's on the road when you're driving into the sun. The brightness of the star will overshadow the brightness of the planet, no matter how big the planet is. So we can do some things to try to make this process easier. One of the things we can do is we can block out the light of the star with just a little linear, a little crosshair in our telescope, and we can try to see the light reflected off that planet directly. That works in some cases. We have detected a handful of planets this way. When is this going to work the best? It's going to work the best for big planets that reflect a lot of light, and it's going to work better the further that planet is away from its star, because the less likely its light is to be overrun by the light of the star. If you imagine a planet like Jupiter in our solar system, if you were in another solar system, it would be way easier to see Jupiter than the Earth, right? Because it is bigger and reflects more sunlight, and it is further away from the sun. This is an important thing to keep in mind when we talk about detecting planets around other stars. The method we use is going to bias us towards detecting certain kinds of planets. So this method is most useful for detecting big planets in big orbits. But we've only detected about 25, 26 planets this way. It's a relatively small number. I will also say that this method works particularly well in the infrared when the planets are still forming and they give off lots of light. When we saw how planetary systems form, one of the images we saw was of the Beta Pictoris system, which is a relatively nearby star with the planetary system that is still forming, and we could see the infrared light being given off by those protoplanets in the protoplanetary disk. But the list is still very, very small. A better method is to look at the influence that a planet has on its parent star. We think of the sun is sitting still and the planets all going around the sun in a circle, but that's not exactly true. Two planets, or two objects, any two objects in the universe, exert a gravitational force on one another. Yes, the sun exerts a gravitational force on, say, the Earth, but the Earth also exerts a gravitational force on the sun. And as a planet moves around a star, that star doesn't just sit perfectly still. The star actually moves around in a small circle. The planet and star together actually orbit around what is called the barycenter, the center of mass of the system. If you imagine a big seesaw, the barycenter is the place where the star and planet would balance on that seesaw. Now, stars are very massive and planets are very tiny, right? So that point is usually inside the star, but the star still moves around a little bit. This is true of any orbit. The moon around the Earth causes the Earth to move around a little bit. The planets around the sun cause the sun to move around a little bit. So if we look at a star and there are planets going around it, that star will actually move around slightly. Now, this motion will be very small. It won't be anything that we could see with our telescopes. But remember, we have a tool in our astronomy tool bag that allows us to measure velocities of an object that's moving either towards us or away from us. And that tool is the Doppler shift. If a star is moving in a little circle and we take a spectrum of that star, sometimes the star is moving towards us, in which case the spectral lines of that star will be shifted towards the blue shifted. And sometimes that star is moving away from us, which means the spectral lines of that star will be redshifted. So as the planet pulls the star around in this little circle, the star is sometimes moving towards us, sometimes away, sometimes towards, sometimes it's away. So the spectral line should be a little blue shifted, a little red shifted, a little blue shifted, a little red shifted. And if we pick one of the wavelengths, one of its spectral lines, and we graph it over time, we should get something that looks like this. A little, let's see, if this is wavelength, longer wavelength is redder. So a little redder, a little bluer, a little redder, a little bluer over time. And if we measure the amount of time it takes a planet to go around a star, we can learn something about the properties of that star's orbit. And we can even, by measuring how much this star is yanked back and forth, make a pretty good guess of what the mass of that planet is. So this is called the Doppler shift method, or the radial velocity method, the velocity of the star towards us or away from us. We can detect exoplanets this way, but again, the method of detection will bias us towards detecting certain kinds of planets. What kinds of planets is this method going to be good at detecting? Well, if it's measuring how much the star is yanked around by the gravitational pull of its planet, then that's going to work best for really massive planets. And it's going to work better the closer that planet is to its star. So this method is going to be biased towards detecting massive planets in close orbits, which means that some of the first planets we detected, some of the first exoplanets we detected ever using this method, were very unusual compared to the planets in our solar system. Here's what actual data looks like. The points are the actual measurements of the velocity towards or away from us of the star, the dates on the horizontal axis, and the dotted line is a fit of, it's actually a sine curve to that data, and you can see the stars moving away from us, towards us, away from us, towards us over time. Here's an example of a planet that was discovered this way, 1995, so a long time ago. The planet is called 51 Pegasi b. The star is called 51 Pegasi. The way we name exoplanets is the name of the star, and then B, the star is A, and then B, C, D, E, F, G for the planets in order away from the star. So here is 51 Pegasi b. It is a planet that has half the mass of Jupiter. So this is a big planet. But its location, so by the way, 51 Pegasus is a star that's pretty similar to our sun. It has a mass of 1.06 solar masses, so just 6% more massive than the sun. And it has a luminosity of 1.3 solar luminosity, so about 30% brighter than the sun. The distance between 51 Pegasus, the star, and 51 Pegasi b, the planet, is 0.01 astronomical units. That's 1% of the distance of the Earth to the sun. And the period of that planet, the year of this planet, is 4.5 days. So this planet goes around its star in less than 5 days, less than a work week. Even Mercury in our solar system takes 88 days to go around the sun and is about 0.3 AU from the sun. So this is the first so-called hot Jupiter that we discovered, a very massive Jovian-type planet located in a ridiculously close orbit to its star that looks nothing like any of the planets in our solar system. As I said when we talked about solar system or planetary system formation, before 1990 or so, our solar system was the only example we had of a planetary system. We would have never guessed that other planetary systems could have Jupiter-like planets and Mercury-like orbits. So this was surprising. But keep in mind that the reason this planet was the first one discovered using this method is because this is the kind of planet that this method is ideally suited to detecting. Really massive planets located really close to their star. That doesn't necessarily mean that hot Jupiters like this are the most common kind of planet. They are just the most easily detected kind of planet using this method. As I said, I looked up on Wikipedia today how many planets we discovered this way. And look, you may have professors that don't let you use Wikipedia for a paper. I would never write a paper using Wikipedia, but for factual information, it's a perfectly good place to look something up. Although you notice that the article does say, hey, this hasn't been updated since 2020, so maybe go looking for a better result. But according to this article, there are only about 31 confirmed planets detected using the radial velocity method. So a very, very small list, and it's a very, very, like I said, bias. Is bias the right word to use? We have the way we use bias in everyday language is a little bit different from the way we use it when talking about scientific results. But this is let's call it a very targeted way of detecting planets. You are detecting planets, but you are detecting a specific kind of planet, a planet that is massive enough and close enough to yank its star around a lot. So you're going to miss a lot of Earth-like planets and Venus-like planets and Mars-like planets that aren't massive enough to pull their star around with their gravitational pull. Some of the more Earth-like planets discovered using this method, Gliese 581 system, we've actually discovered 3 planets in the Gliese 581 system, 3 planets located within about a third of an AU from their stars. So the planets are very different from one another. There we go. Gliese 581b has a mass of about 16 times the Earth's mass, and it orbits in a 5-day orbit around Gliese 581. By the way, Gliese 581 is a red dwarf, an M-type planet, M-type star. So we can think of 581b as being sort of a hot Neptune. It is as massive as Neptune, but it's in a very closer than Mercury orbit to its star. Now, its star is dimmer than the Sun, but we're still in a very, very close orbit. What's next? 581c. I don't know why these slides are changing so slowly. There we go. 581c is a terrestrial size planet. It's about 1.5 times the mass of the Earth. It is located in what would be the star's habitable zone, meaning that it's possible, if the atmosphere was just so, that a planet like this could have liquid water on its surface. Although it's so close to the star that we expect that 581c might be more Venus-like than Earth-like. It's a little too close. And then 581d, which has a mass of 7 times, almost 8 times more massive than the Earth, and very close to the outer edge of the habitable zone of this tiny, red, dim, cool star. We don't have any planets like this in our solar system. 581d is sometimes called a super Earth. The Earth is the most massive terrestrial planet in our solar system. There are no planets with a mass between Earth and Uranus and Neptune, the ice giants. So 581d is a completely different kind of planet that we don't have in our solar system. What would a super Earth like? What would a planet be like that was 7 times more massive and sort of maybe 3 times bigger in radius than the Earth? We don't have a good example of that. What would its plate tectonics be? How long would it take it to cool? We don't know. So the more we learn about exoplanets around other stars, the more we learn that the types of planets that we're familiar with in our own solar system are not the only kind of planets out there. I'll talk about one more method of detecting planets, and that is a method called photometry. Photometry just means photometry, measuring light, measuring specifically the brightness of light. If you've got a planet going around a star, and that planet is lined up just so that it sometimes passes between the star and us, that planet will cause the light from that star to dim. If we measure the brightness of a star very, very accurately, we should be able to see that dip in the star's brightness when a planet passes in front of us. Now, again, this way of looking for planets is better for big planets, right? Because the bigger the planet is, the more light it's going to block of the star. It's also better for planets that have a relatively short orbit around their star, because Otherwise, you'd have to watch that star for 10, 20, 30 years to catch that planet passing in front of it. How much of a drop are we talking here? Sometimes I give a little back-of-the-envelope calculation. Suppose you were in another star system 30 light years away from the sun, and you saw the Earth pass in front of the sun. How much would the sun's brightness dip by being blocked by the Earth? The answer is something like 1 part in 10,000. So in order to measure this dip in brightness of a star caused by a planet passing in front of it, we have to be able to measure the brightness of a star to detect small changes 1 part in 10,000. That's 0.001%. That's hard to do, and it's impossible to do from the ground because the atmosphere will cause fluctuations in brightness of a star by much greater than 1 part in 10,000. So we have to build a telescope up in space to look at stars and to measure their brightness very, very, very accurately. The other thing that this method is going to miss is it's going to miss any planetary system that looks like this. If we're looking at the planetary system from the top or the bottom, so the planets are going around the star this way, they don't pass in front of the star. We only are going to see planetary systems that happen to be just lined up so that the planets from our point of view pass in front of the star. So this method is going to miss a lot of planetary systems that don't happen to be lined up with our line of sight. So we just have to keep that in mind. A planetary system that is we're looking at from above like that, we're never going to detect with this method. We have to use other methods. The most notable instrument for using this method of exoplanet detection was a satellite called Kepler, named after Johannes Kepler. Launched in 2008. The mission lasted from 2009 to about 2018 when it just sort of ran out of fuel to continue its ability to point itself in the right direction. The Kepler satellite was not a particularly powerful telescope. Nobody posts cool images from the Kepler telescope online because it wasn't built to take pretty pictures like Hubble. It was built to look at a little patch of sky and to measure the brightnesses of all the stars in that patch of sky very, very, very accurately. This is what the telescope looked like before it was launched. You see that the primary mirror, well, that's the cover to the mirror, but the mirror is at the other end. It's about the same size. Is smaller than a person, so the primary mirror is maybe 5 feet in diameter. So nothing like the Hubble Space Telescope in terms of its power, but this telescope isn't built to look at other galaxies and stuff. It's just built to look at nearby stars in our galaxy and to measure their brightness. These are some sample transit light curves for planets at different sizes moving at different speeds. How long the dip lasts will tell you something about how fast the planet is moving, which can let you compute its orbit. So even tiny Earth-sized planets will cause a noticeable dip in the brightness of a star as Kepler watches it. Exoplanets discovered by Kepler are just given a number in the order that Kepler discovered them, and then a letter for the planets A, B, C, D if there are more than one planet in a system. This is actual data from Kepler showing this is the normal brightness of the star, and every once in a while it dips, 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 and notice the dips are regular because every time the planet comes around in its orbit, it causes the light to dip. The scale on this horizontal axis is just a few days, so this is a planet in a very rapid orbit. Why? Because the first results that Kepler satellite got were the ones where you only have to watch the planet for a couple of days in order to see it come back again. So the first things that were discovered were, again, big planets in close orbits. Here's a more complicated light curve showing a more complicated pattern, and what this pattern suggests is that there's probably multiple planets passing in front of the star, and we've got to look at the star system for a longer time to figure out how many planets there are and what their various cycles are. These were the first planets discovered by the Kepler mission. Here are Jupiter and Earth just for comparison, and you'll see that the first 4 planets discovered by the Kepler satellite were bigger than Jupiter. Does this mean that there are lots of planets bigger than Jupiter? It might mean that, but what it probably means is this satellite is particularly good at detecting Jupiter-sized planets and bigger, just because of the way the method works. Since then, and the first results were like 2009 or so, since then, in its first 2 years of operation, let's say, the Kepler satellite discovered almost 1,000 planetary systems around other stars. After looking at 156,000 stars, it discovered almost 1,000 that had potential planetary systems. Different sizes of stars, different sizes of planets. That's a total of 1,235 candidate planets, because some of these systems had more than one. About 68 of them were terrestrial sized, between the size of, say, Mars and 3 or 4 times as big as the Earth. And a handful of them, maybe 50 or so, would be located in what we would call their star's habitable zone, that region where you can imagine there being liquid water on the surface the way the Earth has liquid water on the surface. For a couple of years, from say 2011 to 2015, at least once every couple of months, you would see a news story that said, most Earth-like planet ever discovered, because the Kepler satellite was discovering more and more of these terrestrial-sized planets, many of which were in their star's habitable zone. So the amount that we knew about exoplanets went from, say, 20 in 1998 to 1,200 in 2011. Since then, the Kepler satellite has discovered many, many more planets. This is just a visualization showing all the different sizes of stars, and the black dots represent the planet, up to 1,200 candidate planets in the first few years of operation. By the end of its mission, Kepler discovered almost 4,000 or 3,600 planets in 2,700 star systems. About 550 of those planets, terrestrial type planets like the Earth, Venus, and Mars. And 9 of those terrestrial rocky planets could be in their star's habitable zone. So we've gone from only knowing about a dozen or so planets, period, to knowing about 9 or 10 planets that could be Earth-like in their habitability, and thousands of planets in general, and thousands of planetary systems. This is a huge advance in our knowledge in the past 20 years. We've gone from knowing almost nothing to a great deal about what other planetary systems are possible and what other types of planets could exist out there. The next step is to learn more about those planets directly. James Webb Space Telescope has started that process by doing spectroscopy of a known Jovian planet around a nearby star. So we can start to learn things about these planets' atmosphere and composition, and start to learn more about them. And maybe even we can imagine doing spectroscopy of one of these terrestrial planets in the habitable zone. Suppose we detected oxygen in its atmosphere. Suppose we detected changing seasonal levels of CO2 and methane in its atmosphere. We can imagine, indirectly at least, discovering evidence of life around one of these exoplanets in the next 20 years. Maybe not detecting what that life is exactly, but detecting that this planet has something that looks an awful lot like a biosphere, the way the Earth has. I'm not going to talk about all these systems in a great, obviously if there's 2,000 of them, I can't talk about all of them in great detail, but as I said, every couple of years from 2011 to 2017, you would hear about the most Earth-like planet ever. So here's the Earth, and here are several, these, by the way, aren't photographs, right? These are just paintings showing the size of the planet. They're just artist conceptions. But many, many planets discovered around the size of the Earth, but some of them in very different systems. Here's just one example. This is the Kepler 11 system. That's just the 11th discovery that the Kepler satellite made. That's not the official name of the star. The Kepler 11 system has a bunch of planets all inside what would be the orbit of Venus and our planetary system. Kepler 11b, c, d, e, f, and g all located, well, B, C, D, E, and F, all located closer to their parent star than Mercury is to our star. And if you look at the properties of these planets, you've got a planet with 4 times the mass of the Earth, a planet with 6 times the mass of the Earth, a planet with 2.3 times the mass of the Earth, big terrestrial planets that we don't have in our solar system. So what would these planets be like geologically? What would their composition be like? We don't really know. So we have a lot to learn about exoplanets. The successor to Kepler is a satellite called TESS. TESS stands for Transiting Exoplanet Survey Satellite. Transiting means when one thing passes in front of another, so this is using the same method, that the photometry method of detecting a transit of a planet in front of its star. The TESS mission started taking data in 2018. It was officially over in 2020 in terms of its planned mission. It was still working, so that mission was extended until, last I checked, September of 2022, which is just a couple months from now. Will it keep going after that? Will the satellite still keep working? I don't know. The question I will give you guys for an assignment for homework is to give me an update on the TESS. What did it discover? How many planets did it discover? And how do its discoveries compare to the discoveries made with Kepler? Can it discover smaller planets? Can it discover planets with longer or shorter periods? So I will put that up as a separate assignment. So we now know that there are at least, well, what have we learned in the past 20 years that's important? We assumed before 1990 that most stars have planetary systems, but we did not know that for sure. Now we do know for sure that most sun-like stars have planetary systems. That is established. We expected before 1990 or so that most planetary systems kind of look like ours. Little rocky planets in close, big Jovian planets out, and then some icy stuff around the edge. That's not really right. There are a lot of planetary systems that look really, really different from ours. Hot Jupiters, super Earths, things that we don't have in our planetary system at all. So we have a lot to learn about the possibilities for planetary systems. And we also expected that it might be common, or at least not unusual, to have an Earth-sized rocky planet located in its star's habitable zone. We are seeing now that, yeah, it's common enough. We've detected a few dozen possible Earth-like planets. When I say Earth-like, all I mean is terrestrial size and mass, located in a place where water wouldn't definitely be ice or definitely be vapor. You can imagine, if there's the right atmosphere, enough atmospheric pressure to have liquid water on the surface. This raises the next question, is to start thinking about habitability. Can we imagine the processes that led to life on the Earth taking place on these planets around other stars? How common do we think life might be outside of the Earth? We are in the same position with respect to that question as we were with respect to planetary systems in general just a couple of decades ago, which is we have one example of a habitable planet, Earth. We have a few other examples of planets that we think, or objects that we think could be maybe kind of habitable or maybe used to be habitable, like Mars or Europa or Titan or Ganymede or Enceladus. But we're not sure if they're inhabited, and they're probably not, but it'll take another 50 years or so for us to check them all out and see. We have to be very careful drawing generalizations from one data point. I've mentioned this before. But it is unavoidable when you only have one data point to try to make as much sense as you can of the one data point that you have. So what we'll talk about in later videos is the question of extraterrestrial life and habitability, and what kinds of considerations we have available to us as scientists right now, and the early part of the 21st century, to start trying to ask and answer the question about how common extraterrestrial life might be in our galaxy and beyond.